So, my name is Mladenov and this is Christian Mainka. We are PhD students at the university in Bochum. Christian is a co-founder of Hackmanit GmbH, and this is a joint work with Tobias Wich, who implemented the tool we present at the end of our talk. The talk today is about, well, the security of OpenID Connect. Which one of you knows about OpenID Connect? Ooh. And which one of you use Google, Facebook, PayPal? I guess everybody. So this is about the security of the protocol running behind in the communication. So at the beginning, we had three simple questions about the security. The first one was, are old known or known attacks addressed in the OpenID Connect? We have great experience with protocols like SAML, Browser ID, OAuth, and OpenID. And we asked ourselves, can we learn something from the attacks we already know, and can we adapt all this stuff on OpenID Connect, or maybe come with new idea? And we will show yes. And the second question was, are all these issues we know about already addressed in the OpenID Connect specification? Some of them are, some of them are not. The second question was, how secure are current libraries implementing OpenID Connect? Initially, we choose libraries officially referenced on the homepage of OpenID Connect, and evaluated their security. And the third one was, okay, we have some libraries, maybe we found some vulnerabilities, but what is the reason for these vulnerabilities, and how can we bring the development of single sign-on libraries closer to the developers or to the state-of-the-art security issues? Is there any opportunity to make some tool or service which makes for developer the life easier by just running a test and the tool says, yes, you're vulnerable, or everything we know about OpenID Connect and all vulnerabilities, you're secure against all of them. So that was the third question. The plan today is, well, I take the boring part of the talk, introducing OpenID Connect. I apologize for that, but we need this basic stuff in order to explain the attack later on. And the interesting part of the talk will be taken by Christian. The first I want to explain the difference between OAuth and OpenID Connect, because there is misunderstanding in the world. OAuth was designed not for authentication, but for authorization. Authorization is I authorize some web service, web application, or some mobile app to access my resources on a third party, for example, Facebook, Google, and so on. OpenID Connect was designed for authentication, and authentication, I'm authenticating on a client, web service, web application, and I'm presenting my identity, and I can access some resources on this client. This is the main difference between OAuth and OpenID Connect. Is this clear? Perfect. So, what about OpenID Connect? Who uses OpenID Connect? Many of you already know this window or this login opportunity, sign in with Facebook or sign in with Google. If you click on sign in with Google, you will you will be redirected to Google, and behind OpenID Connect is executed. Another option is, for example, on OpenStreetMap, we have multiple identity providers which I can choose to log in with on OpenStreetMap. This can be Yahoo or, again, Google. Another option is on OWASP or Amazon Web Services. Here you can see we can configure our own identity provider which we can use. For example, we can here enter Google, and we will be redirected to Google in order to authenticate and get back to our Amazon Web Services. So, in OpenID Connect, we have three parties. an end user starting the authentication on a client. The client has some resources which are restricted and the authentication is required, and we have an honest OpenID provider, for example, Google. Before we can start with the authentication of our end user, there is one important step, and this is the manual registration. Usually, the client has to register on Google or on the honest OpenID Connect provider in order to establish some trust relationship. Basically exchange key material and further URL information. On Facebook, both for OAuth and OpenID Connect, this phase is identical. The client or the developer of the client register the URL where the web application is deployed, and he gets as response a unique client ID and client secret identifying this client. Another option is presented here, but imagine your URL where your client is deployed changes a little bit. Well, you have to do every single time the registration manually again and again and again, and it could be annoying. Another option is, or another problem is, if I want to use as an end user another OpenID provider, for example, not Google, but my own, how this can be done. And the guys specifying OpenID Connect find a very good dynamic solution which is working on behind dynamically without any user interaction. And I will present this feature. If a user wants to authenticate on the client, he enters his identity. For example, alice@honestop.com. Based on this identity or on the domain, you can see here, honestop.com, a discovery is started. Basically, the client does not know anything about this honest OP, and he tries to figure some further information out. And this is done in the discovery phase. In the second phase, the dynamic registration takes place. The same as in the manual registration, we exchange redirect URI and receive client ID, client secret. Please note, this is a direct communication between the client and the honest OP. The end user does not know anything about these steps. The first step he sees is in phase 2, the user authentication. In this phase, the user will be redirected to Google, and usually you receive or you get the window pop-up, window prompting for authentication on Google with username and password. And in phase 3, the user authenticates on the client. Till now, the most security researchers concentrated on phase 2 and phase 3 because these phases are the most critical. The authentication token is exchanged. But we asked ourselves, what about the first 2 phases? Can we use this stuff for attacks? And the answer is yes. But in order to understand attacks, we will take a look at the discovery. In the first request, based on the extracted domain, we call a URL. And as a response, we receive another URL. This is this href parameter. This is the URL where the further information about the OpenID Connect provider is stored. So what happens? In the following step, we call this URL and retrieve this information. What is in this metadata? Basically, all important URLs which will be called later on. For example, the identity of the honest OpenID provider, or the registration endpoint called in the next phase, or the authorization endpoint. This is the URL where the user will be redirected. Further information like supported algorithms, supported flows, and so on is contained in this metadata too. So the client knows everything about the OpenID provider. The next step is he tries to register. And this is done via dynamic registration. The client sends a registration request containing usually only a redirect URI. This is the URL where the client is deployed. And as a response, he gets a unique client ID and client secret. We are done. The trust relationship is established. We can proceed with the authentication of the end user. And this is done in phase 2. The user will be redirected with the authentication request to the authorization endpoint. This is, again, the pop-up window of Google prompting you for authentication with username, password, or something else. As parameter, the client ID, redirect URI, and scope are sent, and a couple more parameters, but I don't want to confuse you. But basically, now the honest OP knows, okay, this client redirects a user and requests an authentication. In the scope, we can ask for further information about the user, for example, gender, email address, phone, and so on. The user authenticates, and a code is sent back to the client. The code is just a random string referencing to the data fetched in the next phase. We're done. We have a random value on the client, and what happens in the next phase? This is the phase 3, where the user is authenticated. The client uses this code together with the received client ID and client secret, and as in the answer or in the response, he gets the access token and an ID token. The ID token is the most important part because it contains all the information about the user. We will now see the structure of the ID token. The client validates this ID token, and if needed, via the access token, he gets more the resources defined in the previous step in the scope. So for example, phone, gender, and so on. And he gets these resources. Finally, we are logged in. Pretty much communication for one authentication, right? And very phases we can attack or we can start on. So what about the ID token? We have here some information about the user. Let's take a look at this. This is an ID token. It's a JSON web token containing base 64 encoding and consisting of 3 parts. Header, containing all the information about the use algorithms for signing. Body, containing all the information we need about the user. And the signature, which should be verified or must be verified. So, about the body, we have some is parameter. What is this about? About the identity of the OpenID provider which we used. And the subject is our identity on this OpenID provider. And according to the specification, the user's identity is a combination of the issuer and the subject. Please remember this. We need this for the attacks later on, okay? Well, timestamps, issued at, expired nonce. I will not explain the role of these parameters. I guess they're known. And the audience, the ID token is restricted to only one audience, and this is the client for which the ID token was issued for. And that's all. That's all the information we need to authenticate a user. So, now the interesting part of the talk, the attacks.
The mic.
Oh, yeah.
Okay, so we're now going on with attacks on OpenID Connect. And to do so, we first define our threat model that we use to describe our attacks. So we used the web attacker model, so we do not assume any network control. We do not need to break TLS. We just assume that we have an attacker, he has a browser, he can set up some server, he can buy some domain, so nothing very special. He can post on forums, he can send emails, so he has just very, very common techniques to do. Okay, and we will categorize the attacks that we show in 2 parts. So we have category A attacks, which means that there is some interaction of the victim needed. So for example, the victim has to click on some link. Or we have category B attacks, which means there is no interaction at all. If such an attack works, the victim does not get notified that there was an attack. We can simply steal his identity, we can log in with his identity, and the victim cannot do anything against it. So for our attacks, we used a new approach, which we call the attacker identity provider approach, which is based on a very simple fact. So OpenID Connect is, as the name indicates, open. And like Wladenov told us, open means anyone can set up its own identity provider. So the attacker can do this as well. He can set up his own identity provider. And what's now interesting about his own evil OpenID provider is that it has the same endpoints: a discovery endpoint, a registration endpoint, a token endpoint, and so on. So it works like an honest identity provider, but with one important difference. The attacker IDP can manipulate the protocol. So it does not necessarily behave honest. It can drop one message, it can change some parameters, it can just influence the protocol as it likes to do. So what happens if you try to log in with some attacker identity provider, you can start discovery, and then you can, in the discovery phase, decide if you want to register on the attacker IDP, or maybe you want to register on the honest IDP. And it's the same for the second phase. So either you can authenticate on the attacker identity provider, or you can go to the honest identity provider. And for the third phase, it's the same. So you can influence the whole protocol, and this is what we use later on for attacks. Okay, so at first we will have a look at what we call single-phase attacks. So single-phase attacks are basically very simple attacks which only manipulate one single message. So they are very, very simple because of only a few changes to the protocol. So we have again a look at the ID token, and as we have learned previously, the identity of an end user is determined by the combination of the issuer and the subject. And what we are doing in identity spoofing attacks is we try to forge this value. So we create manually a crafted token, and we change these values, and look what happens. And if this attack works, we can forge arbitrary identities. We can log into arbitrary service provider with some victim identity. So we have a category B attack. So there's no interaction of the victim. And how can we do this? So in the OpenID Connect protocol, we have an identity token that is transferred in the third phase of the protocol to the client. And what we are doing is, usually if an OpenID Connect token is created, for example by Google, it contains the issuer parameter, which is of course set to Google because Google creates it. And there is some subject, for example, Alice. If I use my own attacker IDP and I don't do any bad things, I set the issuer value to attacker.com and the subject to something else, for example, Alice. But these two identities are totally different and represent different identities on the client. But what we can do, because we are an attacker, we can do anything we want, we just change some value. So we set the issuer value, although the token is created by the attacker IDP, we set the issuer value to, for example, Google. So if you just send this token, to this client, it will look for the client identically to this token. So it cannot distinguish who really creates it because the token itself says it's created by Google, but it's in fact not. And that's the very simple and, let's say, stupid idea behind identity spoofing, but it works. Another attack that we have found is, so we are going through all parameters in the body right now. So we have seen ISS and subject, and we're now having a look at the audience parameter, which represents the target for which the ID token is going to be used. And let's suppose we have some victim, some end user, and we offer some service like win a free iPhone, because everyone likes free iPhones. So what basically does is the end user logs in, and at some point of the protocol, there is he transfers the token to the client. And the client receives this token, so nothing bad, he can log in. So we have freeiphone.com, and the audience says this token is for freeiphone.com. Everything is fine. But now suppose that it's not a free iPhone winning service, because there are no free iPhones. Let's think there is an attacker who set up this web page, and he can just use this token. So he takes this token and he wants to log in on a different client, on some honest client. And what he basically does is he can use this token and send it to another client during the protocol flow. And this is an implementation flaw, because the client should or must check that the audience is for free iPhone, but the client is honest client, so it's different. It's a different token. And it should be rejected, but if not, the attacker can log in with some identity of the victim. Okay, of course, we looked at replay attacks because this is, I think, easiest attack that we are aware of, and it's so old, so we thought, okay, what can go wrong? So replay attacks are not that difficult to understand. So in OpenID Connect, we only have 3 values representing the freshness of a token, which means we have some expiration time, we have some issued at times, so when the token is created, and we have some nonce value, and you have just to check those 3 values if they have proper values, and then you can easily prevent replay attacks. But in fact, it is still possible because developers simply don't do the checks. I won't go into the details of replay attacks. We'll have another look at signature bypass attacks. So in the last 3 attacks, we looked at all the body parameters, but what we miss is the signature itself and, of course, the header parameter. So, of course, it is important to validate the signature at all, because if you don't check a signature, you have no signature, of course. But there's also some interesting idea if you look into the header. So basically what we have in the header is there is an algorithm defined. Okay, algorithm, that's great. So we can use RSA or HMAC or whatever, and there's a list available of supported values. So we have had a look at the RFC, and there are some interesting values. So we have, for example, HMAC with char and so on and so on. And we look down and down and down, and we find, whoa, there is also support for no signature. So what we can basically do is we take this token and change the value from the original value to some other one. Or we just craft our own token and say, well, we don't need any signature, because why do we? This is quite interesting. It's an attack I think it's found some years ago, but it's still working on some OpenID Connect implementations, or we identified them and we contacted the developers to fix this. So these were single-phase attacks. They were quite simple, and I told you that the attacks in the single phase, they are all mentioned in the specification. So if you, as a developer, follow the specification correctly and very precisely, you will not be affected by this single phase attacks, because they are just stupid implementation flaws. So let's have a look at more complicated attacks. So what we do is cross-phase attacks. And by cross-phase, we need the whole protocol flow. So we're manipulating more messages. The basic idea is when we start such a discovery, on an evil identity provider. So what can go wrong? Is there anything that we can do? And when we have a deeper look into the responses that we have shown previously, we see that in the last step of the discovery, we have some interesting values. So for example, we return some issuer value. It's basically used for the ID token verification. So if you implement OpenID correctly, ID spoofing, as I showed you, is not possible basically because of this parameter. But maybe we can manipulate it at this step. Another thing is the endpoints. They influence the whole phase that will follow. So you can influence the whole protocol flow and do things. And we will now have a look at such an attack. So we have described 3 different kind of cross-phase attacks. So we have created some issuer confusion attack. I want to talk about it. I will have a look at the second one, at the IDP confusion attack, which works as follows. So suppose we have an end user, and what we are going to do is he logs into some client. And then the discovery phase takes place. So what the end user is now doing is he registers on our own attacker IDP. The client registers on this attacker IDP, and he receives some client ID and some client secret. And in the next step, the client is redirected to the evil identity provider with the same client ID that was registered before. So there's no attack at this moment. We just want an end user to log in with some attacker identity, maybe by using a CServe attack or whatever. So he logs in. But now we do something differently. We're just starting a redirect. And we redirect the end user to its own IDP, to an honest IDP. And here is the trick. So during the registration, we can, as an attacker IDP, decide which value we choose for the client ID. And what we are doing is we use the same client ID that the client is using on the honest OP. So this one is the same. And now the end user is redirected to the honest OP. And because it's a redirect, it's transparent for the end user. He cannot see that he was redirected from one IDP to another. He just sees, oh, I can log in at Google or at some other site. And of course he does, well, because he wants to log in. Okay, so he logs in. And then we get a further redirect so that the code is redirected to the client. That's common OpenID Connect protocol. But what you have to know now is the client itself thinks it is using the evil identity provider. The end user thinks to use the honest identity provider. So because we have the client thinking about the evil identity provider, he uses this code and sends it to our own identity provider. And what we basically now have is we have a code, we have a client ID, and we can use it for a further login attempt and can basically get all the data, so there's nothing left that we need to perform the attack. Okay, so the attack concept of attacker IDPs is known since 2012. So Vladi and me, we use it since 2012 to write some research papers. And in 2014, OpenID Connect gets standardized. So we had a look at February 2014, we had a look at OpenID Connect, and we started looking at it and said, oh, what can we do when we have such an attacker IDP? And we reported some issues to the OpenID Connect specification work group and to the OAuth working group that say, okay, there are some problems when you use discovery and when you redirect and so on. In October 2015, they reacted. They invited us to find some countermeasures. And now in January 2016, there is a mitigation draft that addresses this issue. So what this countermeasure basically does is it takes place in the second phase where the code is redeemed. And what they basically do is, instead of simply sending the code, for example, in this attack here, an IDP should always add the issuer, so that every client knows, oh, I got a code, and I got this code from one specific identity provider. And if we now would like to send this code to the attacker IDP, he would see that it's not matching because there is an issuer of the honest IDP, but I would like to send it to the other IDP, so this is strange, I will stop. Well, it's a very, very easy countermeasure, but it needs some protocol adjustment, so the protocol has to be changed and extended by this parameter. Okay, so there was even more. We had a look at what we call malicious endpoint attacks. So we just thought, okay, there are 3 phases. And during the discovery, we can influence all these phases. So we can manipulate where an honest client would like to go, which URLs it retrieves. And so we thought, what can go wrong? So we have a server communicating to another server. Well, that's nice. We had a lot of talk about server-side request forgery at OWASP, so let's think about it. So what we can basically do is, during the discovery, we can enforce a client to send some messages to servers that we choose. So if there is a firewall or local network, we can, for example, have a look at some local services. We can see if they are available. We can maybe do some port scans. There are a lot of techniques that you can launch with OpenID Connect if discovery is supported. We also thought about, what about denial of service? So just contacting some other service is not enough. So what we try to do is we enforce a client to download some file, for example, some Debian image or some other big file available on the public server. And so what can go wrong? It should be a discovery document of some bytes, but we will receive some very, very large document or very large image file. And we simply tried some logging attempts. So this is a demo application that we have set up. We just tried to log in 5 times in parallel. And this is the normal behavior. This is quite normal. And then we linked it to some Debian image with only 5 login attempts. So nothing special. And we see that there is a huge increasement. And if you are doing this more effective, you can do more login attempts, you can use larger files, or you can limit the download speed. So there are a lot of tricks that you can do to improve the attack. Okay, so we evaluated some libraries. To do so, we basically looked at the OpenID specification page. And we looked which libraries are linked and some of them are certified, some of them are not certified. I don't know what certified exactly means. I think they are looking for features, not for security. So don't mix it up. But there are some libraries, and when we started our evaluation, we downloaded almost all of them. I think there are now some newer ones. And we thought, okay, they are linked. They should be secure because everyone who wants to use OpenID Connect and develop something, what will he do? He goes to the web page, to the official web page, and downloads some OpenID provider or OpenID client in this case that fits his needs, so the programming language, for example. Okay, so we had a look at it, and we at first looked if our attack approach is really working, because attacker IDPs are very uncommon. So we look, can we do this with OpenID Connect? So we look if, do these libraries support custom IDPs, or do they just support, for example, Google? So if they only support Google, we cannot put our own attacker IDP and we cannot launch these attacks. But all of them support custom IDPs, and most of them in 6 cases also support dynamic registration and discovery, which makes attacks just smoother. So if it's not supported, for example, in Drupal it's not supported, then we have to set up our own then we have to set up our own identity provider manually and register it, but that's no big deal. We can do it. Okay, then we had a look at the different attack techniques, and what we found out is we just categorized them here. So we see that, for example, the very simple identity spoofing attack belonging to class B, which means there is no user interaction, you can fake any identity, was working in half of the cases. So it was quite interesting to see that this issue, although it is very clearly specified, that you have to do some checks. It's not implemented in all libraries just because the specification is very long, I think, and there are a lot of things you have to read and to understand. So it's not easy to understand why this is working. And I think although the specification addresses, for example, wrong recipient very clearly, some developers might think, oh, why do I have to check this audience? So is there any reason for it? Because they don't see the attack behind it. What I was really surprised about was that replay attacks were working. So it seems that the libraries do not care much about nonces, about timestamps, and I don't really understand why, because it's mentioned at so many points in the specification that you have to check it, but it seems that they simply just skip it. Yeah, we also tried signature bypasses and some other attacks. On the cross-face attack side, it's very easy to see that specification flaws will work because it's a specification flaw. So even if an implementation does all the right things and follows the specification correctly, an implementation cannot handle this attack because it's a flaw in the specification. So this is not very surprising. Yeah, and we had another attack, the issuer confusion attack, which I didn't describe in this talk, but it was also working on 3 of 8 cases. Okay, so to summarize this up, we found out that for the single-phase attacks, most attacks or all attacks are mentioned in the specification. We found some newer attacks, but we wondered that there were so many implementation flaws. And we thought, what can we do against it? So we created Professors, which is an acronym for Practical Offensive Evaluating Single Sign-On Services. And what we are doing is basically, we have the following scenario. So we have a service provider that we are going to test, and we are some pen tester or some developer, and we want to know, is this implementation secure? Okay, so what we did is basically we were very lucky because we had Tobias, and Tobias is a great implementer, and what he did is he is creating a website which offers a service to evaluate all implementations so that you don't have to install anything. And Tobias' tool works as follows. First, you have to configure it. It looks very complicated at this point. So there are a lot of things that you can configure, but what you have basically to do is to log in some URL. And I think a lot of people of you are using one-click solutions for penetration tests, and you might have seen that one-click solutions are not always the best one. So they are giving you some results, but in more complicated tasks or in scenarios where something is different to others, you have to adjust some parameters, and sometimes it's not possible. So what we did is we tried to identify things or parameters that makes the testing easier. So for example, you can submit your own Selenium script, which is used to log in. So what the tool has to do is to enter some URL, press the enter button, and log in. And if it cannot determine this automatically, you can simply submit your own Selenium script to do this automatically. It's also good to know that we have some user profile URL here, because we coped with one problem. When we logged in with identity, we could not see which identity is used. So is the victim identity used or is the attacker identity used? And For this reason, we created some what we call user profile URL. So the tool will go to some specific URL, for example, the profile URL where you can see the email address, and you can then distinguish two accounts. Okay, so after the configuration, we use attacker IDPs. Initially, we started with only one attacker IDP. And we found out it's not that easy because when you, for example, try to log in with some Google identity, you cannot see the traffic between the service provider and the Google identity provider because our attacker model assumes that we don't control the network. So what we do is, instead of using Google as an honest IDP, we use our own honest IDP. So we have two different domains, two different identity providers. One is correctly using the OpenID Connect protocol, and the other one starts the attack. And yeah, basically that's all. So at the end, you get some security report. We are also planning to do tests with identity providers, but that's more or less future work. Here you can see a screenshot of our tool, which is more or less publicly available. So we wanted to make it public, but the specification guys said, oh, it's maybe not the best idea. So if you're interested in, you can write us an email. We are allowed to give specific persons the tool, but it's not possible to make it public at the moment, so we are working on this, how to handle this. Okay, yeah, so that's the current state of Professors. So we have implemented the configuration and learning stage, and security tests for 20 attacks are implemented. They are evaluated automatically. The results are outputted to the pen tester. What we are currently doing is, of course, we have more attack ideas and we have to implement them. And what's at the moment missing is to give concrete advices to some developer what check is missing, where he has to look in the specification and how he can cope with specific attacks. And what we also want to do is we want to do OWASP because it's the basis of our OpenID Connect, and of course, as I mentioned, the security evaluation of identity providers. So to sum this up, the OpenID Connect specification addresses single-phase attacks, but I think it's very easy to say that stupid implementation flaws will always exist. So we had this nice keynote by Charlie, who also talked about bugs. So I think we will always see bugs, and by using a security testing approach during the development, which can be repeated, so that a new version of a library can always be tested, we think that's the best way to improve the security of an important single sign-on protocol or of implementations in general. So we have added some resources for you. So for some attacks, we have another website doing an malicious endpoint attack. We have our blog where we describe some attacks, and yeah, we have also a paper. So thank you for the attention. We are now happy to answer your questions, if there are any.